When we first hit play and watch the bowling ball travel down the lane, it isn't too exciting. The bowler has applied just the right amount of forward rotation to the ball, as evidenced by her selection of initial rotational velocity, for the ball to roll without slipping the whole time. The rotational velocity in this simulation is always expressed as multiples of v over r. In this case, v is the initial speed, so 10 meters a second, and r is the radius of the ball. In this case, it's medium in size. Let's have her launch the ball again, but this time with no initial rotational velocity. This means the ball will initially be sliding along the lane, with friction both slowing it down in its left to right motion, but also at the same time causing the ball to begin rotating clockwise. The graph at top shows what is happening. The green line represents the velocity, initially 10 meters per second, but slowing with time. The red line represents the rotational velocity of the edge of the ball, initially 0, but increasing with time. When they match, the ball locks into its rolling. Let's try again, but this time start the ball with some backspin, so initially some negative rotational velocity. Let's choose negative 2v over r. The backspin here is very severe, and it takes a while to get the ball rolling forward again. Over this time, the ball slows down quite a bit and is only creeping down the alleyway. What happens if we reduce the friction coefficient? Let's adjust the slider from 0.3 to 0.1. This means the frictional force will be 1/10 the contact force with the surface of the lane, fairly low friction. We see that the ball takes a really long time to slow and reverse its spin, as we'd expect. Let's turn on the force diagram and repeat the same trip. We can see the contact force upward on the ball. This is also known as the normal force. We can also see the gravitational force and the frictional force. A word of caution here. The force vectors are labeled with their actual values, but are not shown to scale. The frictional force should only be 1/10 the length of the normal force vector because the coefficient of friction is 0.1. We found when designing the simulation that this was very hard to visualize to scale. If we turn on the net force rather than the free body diagram, we can see that only the frictional force is responsible for the net force. This is because the upward normal or contact force is exactly balanced by the downward gravitational force. The leftward frictional force is the only thing slowing down the ball. If you divide this force by the mass of the ball, you'll get the ball's acceleration. This should equal the slope of the velocity when plotted versus time. Checking the graph above, we see that a green negative slope is exactly what we'd expect. The torque acting on the ball is the product of its radius and the frictional force. This is a clean product with no sign of any angle involved because the frictional force is always acting at a right angle to the radius vector. This torque, combined with the rotational inertia of the ball, allows us to calculate its angular acceleration. The upward red slope in the graph should match this acceleration when multiplied by the ball's radius. Hitting play, we can verify that the frictional force does indeed disappear when the ball stops slipping with respect to the alley. This phenomenon isn't something you need to wait to go to the bowling alley to see. Try taking a small ball or marble and applying backspin to it on your table. The ball will slip for a bit, but always eventually locks in to rolling without slipping. Check it out, and thank you for watching.